Recently, we've talked about fission, a process where a large nucleus splits into smaller ones and energy is released. Nuclear reaction of fusion also releases energy, but it happens when smaller atoms fuse together to form a bigger, heavier atom. Here we have a reaction between two isotopes of hydrogen, hydrogen 2, also known as deuterium, and hydrogen 3, also known as tritium. Those two nuclei smash into each other and stick, forming a nucleus of helium. Energy is released in the process. An extra neutron that was unable to stay in the newly formed nucleus is released. Now, let's find out where the released energy is coming from. To figure out the origin of energy released in the process of fusion, we need to talk about thermodynamic stability of an atom. Let's consider the isotope of oxygen 16. The nucleus of this atom is made of 8 protons and 8 neutrons, and the mass of protons and neutrons make up the mass of this atom. Here are the masses of 1 proton and 1 neutron. Usually we round them up to 1 atomic mass unit, but for now let's be precise. So if I take 8 times the mass of a proton and take 8 times the mass of a neutron and add them up, I'll get 16.136992 atomic mass unit as my expected mass of oxygen 16. But when I go and measure the exact mass of one atom of oxygen 16, it turns out to be 16 atomic mass units exactly. Mass disappears. That's not supposed to be happening. 0.136992 atomic mass unit might not seem like much to worry about. But if we scale it to 100 moles of oxygen atoms, it is 13.7 grams of mass disappearing. For a long time, we've tried to convince ourselves that it is the defect of measurement, until eventually we had to admit that mass disappears when subatomic particles unite to form a nucleus. The mass lost when subatomic particles unite to form a nucleus is called mass defect. The person who helped to explain and quantify the mass defect was Albert Einstein. Mass cannot be created or destroyed, but in nuclear reactions it can be converted into energy. The amount of energy produced when mass is converted into energy can be calculated through the famous equation E equals mc squared, where E represents energy, m mass converted, and c the speed of light, which is a constant, 3 times to the 10 to the power of 8 meters per second. Considering this equation, you can guess that even a tiny mass, when it is converted into energy, converted into a lot of energy. After all, we're multiplying the mass by the speed of light squared. So, when those 8 protons and 8 neutrons come together to form the nucleus of oxygen 16, some of the mass is converted into energy and mass decreases slightly, while a huge amount of energy is released. If we draw a schematic representation of a potential energy diagram for this process, we would see that 8 free protons and 8 free neutrons have a higher amount of energy compared to the amount of energy they have when they are combined into a nucleus. And this energy, is released in the process of protons and neutrons being united into the nucleus. The energy released when subatomic particles come together and form a nucleus is called nuclear binding energy. It is the energy that keeps protons from flying away from each other. It binds those subatomic particles. This is the amount of energy that we have to spend if we decide to separate protons and neutrons back into their free form. So, if we go back to our example of fusion of deuterium and tritium, the energy released in the process is the nuclear binding energy. Some mass is converted into energy as deuterium and tritium form the nucleus of helium. This is the reaction that is running in the sun. Here are some sample questions. Which change occurs during a nuclear fission reaction? The statement number 4 is the correct answer. Matter is converted into energy. It is actually a true statement for both fission and fusion reactions. The next question. The greatest amount of energy released per gram of reactants occurring during a fission reaction. Fission reaction produces the greatest amount of energy per gram of reactants used in it. That is why it is so difficult for us to give up on nuclear power plants. In terms of amount of energy released, a nuclear reaction beats by far any chemical reaction. What is the one benefit associated with the nuclear fission reaction? Well, let's see statement by statement. The products are not radioactive. Definitely not true. Products of fission reaction are radioactive for centuries to come, and we don't know what to do with them, how to store them, and how to protect ourselves from it. Number two, stable isotopes are used as reactants. Also not true. We use unstable isotopes, and in fact, we make them even more unstable. There is no chance of biological exposure. Definitely, there is a pretty high chance of biological exposure in case of some malfunction. There were tragedies of Chernobyl and more recent in Fukushima, and that shows that it can be quite dangerous. But the large amount of energy produced in the fission reaction, and for that one benefit, we risk it all. Compared to an ordinary chemical reaction, a fission reaction will release larger amount of energy. Which phrase identifies and describes this reaction? Well, this reaction is clearly a reaction of fusion, as we see that two light atoms form a heavier nucleus. And as we discussed before, in fusion, mass is converted into energy. Okay, next question. Which balanced equation represents nuclear fusion? Well, answers 2 and 4 represent chemical reactions, so they are out of the question already. Answer 3 represents artificial transmutation, nuclear reaction, but the newly formed nucleus is not heavier than the reactant, so it is not fusion. And answer 1 is the reaction of fusion. We see two deuteriums fused together to form helium.